Hello there, Lynchburg City students. I am back again. It's me, Tristan Brown. Today we're going to do something a lot different than what we've done in the past, pretty much all of the other videos. Today we're going to look at the formula sheet and all that is on it, all the information, all the different formulas, what they mean, how we can interpret them, how we can use them to our advantage the best. Again, I remember if you've watched in most of the other videos, I usually mention it at some point or another. Um, but the formula sheet itself, it's all the problems that you use the formula sheet for, they all come from that additional topics section. So I know that cumulatively there's only those 6 questions, but they're just so vast. That's why we've had so much content going over questions in that section, just because there's such a large range of content for those 6 questions. I don't want anyone to be left behind on that. So here we are, reading through the formula sheet. So this right here, what you see, or hopefully see anyway, is what the formula sheet will look like when you take the SAT. You'll have your circle, rectangle, triangles, lots of triangles. You have your rectangular prism, your cylinder, your sphere, your cone, and your pyramid. And then it's got these 3 statements down at the bottom left. And today in this video, what we're going to do is just go through everything on this sheet individually, break it down term by term, for at least for the first couple, because we get a lot of repetition through the formulas to the point that we understand it, know how to use it. What you might notice off the bat, if you've looked at most formula sheets, that when we get to these 3D figures, there's no surface area. I've looked because I was curious when I saw that if just you had to know the surface area formulas or they weren't present on the SAT, and I could not find any problems on the SAT that use the surface area. So you do get off the hook there. You only have to know, well, you don't even have to know the volume formulas. You just have to know how to use the volume formulas. So with all of that being said, we're going to jump in. We're just going to go from this top all the way to the end of this row with the special triangles and then go through the 3D shapes. And then at the very end, we'll go through these 3 statements at the bottom. And then we've got a question at the very end of the video that utilizes some of this information. So the circle and its formulas are in any object that is round. You will have this R term for the area and the circumference or the volume once we get to 3D figures. And R is the radius of the circle. The radius is a line segment drawn from the center of the circle to any boundary point on the circle. And that's just the outer rim of the circle. Pi, maybe you knew this, maybe you didn't. Pi is just a constant. A very commonly occurring constant, but it's actually was directly found when pi was discovered. It was found by taking the circumference of the circle and dividing it by the diameter, and they kept getting this 3.141 and so on, to the point that they gave it the Greek letter pi to represent it in circles. So that's actually where that came from. I don't know if you care or knew about that, but I find that fairly interesting. So then this first formula for the circle, we have A equals pi r squared. A represents area in this case. Area for every formula we look through. Area is always a 2-dimensional formula, so the units when you have area are always squared, and I gave the example of centimeters squared. But you can have meters squared, inches squared, or they might say square inches. It can be represented as both the way I have seen more commonly. And then the second formula, C, 2 pi r, is the circumference of the circle, and the circumference is the distance around the circle. So it's like perimeter, but for a circle. That's what that is essentially. It's obviously more complicated than perimeter. You also notice the perimeters were not on the initial or formula sheet. They do presume that you know how to find perimeter. And then area, I did forget to mention this initially, but area is just the space inside of this object. That's how area works. So then rectangles and squares, it shows the rectangle, but obviously any figure of the sort is going to have the same formula for area, which is just length times width. So that's one dimension by the other. And again, it's area, so it's in units squared. So this is non-right triangles. Although the one formula it does have on here will work for right triangles, it just looks a little bit different. A non-right triangle is just any triangle without a right angle. H is the height of the triangle. What you do for the triangle is you take the vertex opposite the, well, I guess I should define base first. Base can be any of the three sides of the triangle. And then based off what you choose for base, you select your height. But so base can be any side. It just uses the bottom side typically is what we call the base. And then height is the perpendicular bisector taken from the vertex opposite of the base and drop down to it. And you'll notice that that even creates a right angle, which if you ignore this left half of the triangle, you can obviously taking the area of a right triangle would be identical. So it works both ways. It just shows for the non-right triangle. And again, this area is for the whole triangle, not just this right portion or the left portion, because obviously it's going to give you the same thing each time, and it's for the triangle as a whole. So then we get to right triangles. The first thing it shows us for right triangles is Pythagorean theorem. I hope most of you know, but Pythagorean theorem says that if we take the two sides adjacent to the right angle, so that's A and B, since they both are along the right angle, if you square each of those sides and add them together, it's equal to the square of the hypotenuse. Even though I haven't went over a problem that uses Pythagorean theorem, I would go out on a limb and say that you will likely get a problem on the SAT that will use Pythagorean theorem in some way. Obviously, they can give you any of the two sides and ask you to find the third one from this formula, whether they give you C and B or A and B, or B and C. Regardless, you can use it as long as you have to find the third. And then the special cases for right triangles. So we have two special right triangles. We have, I'll use the second one first, the 45-45-90 problem, our triangle, which is very convenient. It says if we have a right triangle, an isosceles right triangle, since both of these are equivalent, we have this relation about the sides, and it's that the two adjacent sides are both the same, and that the hypotenuse is just whatever that side is times the square root of 2, which is a very convenient formula to have. And we have a similar case up here for the 30-60-90 right triangle. It's not as convenient or easy to memorize, but they do give it to you on the formula sheet, so you don't have to memorize it. It says the side opposite of the 30-degree angle is x, just any given value. The side opposite of the 60-degree angle is just whatever that value is times the square root of 3. And then the hypotenuse is just double the length of the shorter side x. So they're both very nice. Again, these are trigonometry type problems. They're not hard, you just have to use the formula and go straight through it. So then we're going to get to our 3D shapes. We get the rectangular prisms, and cubes would be included in this as well. But you'll notice, if you remember back to our force formula for a rectangle, it was just length times width. And now for the volume, we're just adding this third dimension of height. Volume, area was in units cubed. Volume is in unit, or excuse me, area was in units squared. Volume is in units cubed. So feet cubed, meters cubed, miles cubed, whatever it might be, they're in cubed units. And that, again, it just multiplies upon what we had with area. It's how much space is inside the object. So that's what volume is. And again, for a rectangular prism, you just multiply the length times width, which is the base of the prism, times the height. And you're going to find that for a lot of these formulas. We're going to take a 2D formula and multiply it by a height. And it's certainly the case with the cylinder. You take the the pi r squared from the area of a circle, and then you just multiply it by the height, and that's how you get volume of a cylinder. Sphere is one that is quite noticeably different because it doesn't have it has one base circle, and then it gets increasingly smaller all the way down, and the same thing the way up. So we can't multiply it by the base itself without having some sort of other relation. And so that other relation is, instead of multiplying it by a height, we multiply it again by the radius, which is why we have r cubed this time instead of r squared. And this 4/3, it's very complicated to explain. If you have to use calculus to drive this formula, and this 4/3 just comes up as a constant from the derivation for the volume of a sphere. It's very fun to do, but it's also very complex. And I'd rather not do anything confusing, and it's hard to do it myself. So I'll leave it at that. That's why the 4/3 is there. It's just a constant that comes up when deriving the formula. And this r cubed is here because we don't have a height that we can consistently multiply by, whereas the radius is consistent all the way through the sphere. Cones. This one's very unique. You'll find that we have the pi r squared from a circle because our cone has a circular base. And it's even multiplied the height like a cylinder would be, but it's 1/3 of that. So you find for our triangular shapes, typically they're 1/3 of our round equivalents of those shapes. It's a very unique relation they have, but you'll find if you have this volume for the cone, it's just 1/3 of what a cylinder with the same base and height would be, which I find fascinating. Maybe you don't, maybe you do. And you'll find that again on our next with the pyramid. Just instead of being a circular base, it has a squared base. So as that length times width from the base square or rectangle, it doesn't have to be square. And we multiply it by the height like we did our rectangular prism. And then we take 1/3 of it to get the pyramid instead of the rectangular prism, which I find, again, I think that's very cool. And then there's if you remember to the formula sheet, there were these 3 statements down in the bottom left corner. And I do honestly believe that whoever writes the SAT just puts them on there to be confusing. I'm going to read them to you because of just how odd they sound. But it says, the number of degrees of arc in a circle is 360 degrees. Put in plain terms, there's 360 degrees in the circle. Why they say, well, I mean, I know why they say degrees of arc, but it's not essential to put that. Everyone knows the circle has 360 degrees. You're not going to use it in any other way. So that's just what that statement means. The second statement's similar, except having both of them combined, we can deduce a little bit. But it says the number of radians, so this is just a different unit of measurement, of arc in a circle is 2 pi. So that means if you go around a circle one time, there's 2 pi radians in it, equivalently to if you go around a circle one time, you have 360 degrees. And from that, we can say that 360 degrees is equal to 2 pi radians. If for those of you that have taken trigonometry, that should hopefully make sense from the unit circle. If not, that's where that relation comes in. I haven't seen any problems in going through on the SAT that have used this, but since they do give it to you as information, they certainly can ask questions about it. And then it tells you lastly, the sum of the measures in degrees of the angles in a triangle is 180 degrees. Obviously, that's a lot of words to just say that a triangle has 180. There's 180 degrees in a triangle. That's all it's trying to say. So it does give you that, which is nice, because if you were to blank on a question, you can actually reference the sheet. It's very useful to have that for those purposes. But sometimes it can also be confusing. So that's why I wanted to go through that. And now I want to do a problem like we typically do. It uses at least one of the uses only one of those formulas. This, of course, is from the additional topics section. I was surprised it said this is a hard problem. I didn't find it to be that bad, but I guess this is what I've been trying to do with my life. So I would like to think I wouldn't find most of these problems hard. And you probably are glad that I don't find most of them hard too, I would hope. So I'll read the problem. Again, you can take whatever time you need to pause the video, try to figure out what you're supposed to do with the question. We'll solve it together, make sure I got the right answer, and talk a little bit about why, and we'll go from there. So it says, a dairy farmer uses a storage silo that is in the shape of a cylinder, and that cylinder is pictured above. If the volume of the silo is 72 pi, what is the diameter of the base of the cylinder in yards? All right. So we've got a couple things in this question. We know from the picture alone that the height of the cylinder is 8 yards. We know that the volume is 72 pi, and we want to know what the diameter is. So if you recall back for a formula sheet, obviously if you were taking the SAT, you could just look at your formula sheet, but the volume for a cylinder is pi r squared h. Okay, so we get that, and it tells us that our volume is 72 pi, so we can just go ahead and fill that in. And that's still equal to pi r squared, except I'm going to go ahead and fill in our height since it gives us that too, of 8 yards. So our first step is to divide 72 by 8. 72 divided by 8 gives us 9 pi, which equals pi r squared. Our pi's will cancel out, so then we're left with 9 equals r squared. Thankfully, 9 is a perfect square, so if we take the square root of both sides, we get that 3 equals r, and that's in yards. So we get 3 yards equals r. So that's our radius. However, the question wants the diameter, so this is one of those where it does ask you to take it that one step further. And of course, diameter is just 2 times the radius, which equals 6 yards. And if we scroll below to the next step, hopefully I did all of that right. And it is, it's 6 yards for the diameter of the cylinder. And then of course the y's, volume's pi r squared h. And it gives us the volume and the height, so we have to work backwards to find the radius so that we can find the diameter. And you'll find most questions that use formulas just ask you to plug in whatever information the question gives to find one piece of information that they won't give you in the question. And they're really more algebra questions than they are geometry or trigonometry questions, but they're still classified under the section because this is a problem that you would typically do in geometry. So that's where all that comes from. I do hope this video was helpful. Again, it's the formula sheet. You have it. Anything that they give you, try to use to your advantage. So I hope this has helped you to gain better understanding over those formulas, why they are the way they are, and that this problem may have even helped. So thank you guys for watching, and I will see you at the next video.